Everyone, I'm Dharsshan here and welcome to my presentation for MEMD 4023, Failure Analysis and Design. Today we'll explore a vital topic in mechanical engineering, the difference between fail-safe and safe life design. To make this easy to understand, I will explain it using an example most of us are familiar with, an aircraft system. Let's begin with fail-safe design. In simple terms, this design method allows for the possibility of failure, but ensures that the system remains operational and safe even after the failure occurs. It's about making sure that the failure doesn't result in disaster. This is done by adding redundancy, or in other words, backup components or paths that can take over when the primary one fails. In aviation, a clear example is the fuselage structure of an airplane. The fuselage is the main body of the aircraft that houses passenger, cargo, and flight systems. It's made up of multiple structural members arranged with overlapping load paths. If a crack forms in one beam or joint due to fatigue or damage, the load is redistributed to nearby structural elements, keeping the aircraft stable and safe. This gives the pilot enough time to land safely and for maintenance crew to identify and repair the damage. In addition, aircraft use riveted joints and layered skins, so a crack can stop at a joint rather than spread across the body, a clever application for fail-safe thinking. Now, let's move on to safe life design. Unlike fail-safe, safe life means designing a component in such a way that it will never fail during its intended life, even once. This is usually applied to components that are highly stressed, cannot be monitored continuously, or would cause catastrophic consequences if they fail even once. In an aircraft, parts like landing gear pins, engine turbine blades, and critical bolts follow the safe life approach. These components undergo intense stress during every takeoff and landing. Because of this, engineers set a strict limit on their operational life, usually measured in flight hours or landing cycles. Once that limit is reached, the part is retired and replaced, even if it appears perfectly fine. This design approach removes any chance of failure by ensuring the component never gets close to its breaking point. Both fail-safe and safe life designs rely heavily on something called inspectability, the ability to detect damage, cracks, or signs of wear through regular inspection and testing. For fail-safe systems, inspections help catch the failure after it happens but before it becomes critical. For safe life systems, inspections confirm that components are removed before a failure even begins. In aviation, highly trained technicians perform non-destructive testing such as ultrasonic testing, X-ray scans, and dye penetrant testing to monitor fatigue cracks in fuselage panels, blades, and pins. This level of inspectability ensures that the system remains reliable over time. To recap the difference, fail-safe design accepts that failure may happen but includes backup systems to keep things safe. Safe life design prevents failure by replacing parts before they become a risk. In a modern aircraft, both strategies are used together. For example, the fuselage structure is designed to be fail-safe while the landing gear hinge pins are safe life. This combination ensures that even if one part fails, the aircraft remains safe to operate. Thank you for watching, and I hope this video gives you a clear understanding of the difference between fail-safe and safe life design, especially how they apply in real-world systems like aircraft. Together they form the foundation of modern engineering of safety practices.